Welcome. In this video, I'm going to go over an optimization problem, and this one is an optimization problem in two parts. There is a part A and a part B. So part A, actually, let's read the full question first. A food storage company makes cylindrical cans with volume of 600 milliliters. That's a cubic centimeter. So what dimensions, height and radius, will minimize the material needed to produce the can? And now this part is assuming that materials for the wall and the top and bottom cost the same amount. So what does that mean? Let me draw a cylinder to make this a bit more clear. All right, so there is a cylindrical can, and the cylindrical wall is all of this, the part that, say, wraps around, and the top and bottom are these parts. So let's begin with our objective and our constraint. Our objective is to minimize surface area. Our constraint is the volume. And this one's a lot easier, so I'm just going to go ahead and write down the volume. B equals 600 milliliters. Now, what is the surface area of this can? So, if you've ever bought any canned goods, maybe you've peeled the label off before. So let's imagine I'm cutting this can, say right here, I'm just cutting it straight down. And I'm going to unroll it on either side. Well, what would that look like? That would look like this rectangle here. And now the top and the bottom of the can would correspond to these parts here. Whereas everything else, say the cylindrical wall versus the top and bottom. Okay, so let's label some things really quick, and then we can figure out what the surface area is. I want a formula for the surface area. So the top here, since this is a cylinder, I know I'm going to have a radius, so this is R. And now this distance around this circle, that's just the circumference of this circle, C equals 2 pi R. So that tells me that this longer side, at least visually right now in this picture, it might not turn out to be the longer side, but in my picture here, along the red side of this rectangle, that distance is 2 pi R. Now, I don't know the dimensions of what my whole cylinder will be, so I'm going to label this vertical distance here. I'm going to label it H for height. So this is my height. So I know that the area here of this rectangle is 2 pi R times H. What about the tops and bottoms? Well, the top and bottom are both a circle, and as such, their area is just pi R squared. And remember, I have two of these. So I need to add up pi R squared plus 2 pi RH. So that gives me a surface area of 2 pi R squared plus 2 pi RH. Okay, well, how can I relate surface area to this volume here? Well, what is the volume of this cylinder? The volume of this cylinder is the area of the base times the height. So its volume can also be given by pi r squared h. So I know that 600 equals pi r squared h, or equivalently, h equals 600 divided by pi r squared. Now I have this function here of r in terms of h. So I'm going to replace this h. And my only variable for this surface area equation will be r. So this is a function of r. And it is 2 pi r squared plus 2 pi r times 600 over pi r squared. So AR is equal to 2 pi r squared. And now notice here I have an r in the numerator and r squared in the denominator. I also have a pi and a pi. So these pi's go away, and I end up with 1,200. Oh, I forgot a plus sign here, excuse me. 1,200 times r to the negative 1 power. Now, I could have also written this as 1,200 over r. But in order to make it more clear what the first derivative is, I left it as r to the negative 1 power. Since the next thing we have to do to figure out a minimum is we need to figure out where the tangent line is horizontal. Because remember, whether we have a max, as this shows, or a min, we can identify those using the derivative by identifying where our tangent line is horizontal. So to do that, we need to find the first derivative and set it equal to 0. So a prime of r is equal to 4 pi r minus 1,200 times r to the negative 2 power. Okay, so now I'm going to set this equal to 0. So this is 4 pi r minus 1,200 over r squared is equal to 0. Equivalently, 4 pi r is equal to 1,200 over r squared. 4 pi r cubed, again, this is equivalent, is equal to 1,200. And so I end up with r cubed is equal to 1,200 divided by 4 pi on both sides. And that gives us 300 over pi. Okay, so now let's just pop this in on a calculator. Please pause your video and get your calculator out. R is equal to the cube root of 300 divided by pi. And that is approximately 4.571. Now, I could use the second derivative to verify that this is a minimum. I did that in my last video. So in this video, I'm going to do something different. So is r equals the cube root of 300 over pi a minimum value. This time I'm going to draw a little mini number line. And here is 4.571. On the left, I have the number 4. And on the right here, I have the number 5. So what is a prime evaluated at 4? And you don't even actually need to get the exact value. All we really have to consider is this positive or negative? Well, I'd have 16 pi minus 1,200 divided by 16. That's definitely going to be less than 0. And here, a prime of 5, I'm going to have 20, that's 4 times 5, 20 pi minus 1,200 divided by 25. And if you don't see this, type it into your calculator, but that's definitely going to be positive. And if you need to see it, this one here is about negative 24.7. This one here is 14.8. This one's definitely positive. So what does that tell us? That tells us that this curve is decreasing than it is increasing. That's definitely a minimum. So since A is decreasing and decreasing here to the left of 4.571, then increasing to the right of 4.571, then we know that this value is certainly a minimum. Now, before we can write out our conclusion, I made some space here because we need to figure out what H is. So this is when R equals 4.571. So that would be 600 divided by pi times 4.571 quantity squared. Please get your calculator out and work that out. All right, you should have gotten 9.141. Well, what are our units? They are in centimeters. Okay, so now we can write out a sentence. And I have some space here to write out our conclusion. The dimensions, which minimize the surface area of this can, are approximately a radius of, and I'll round to one decimal place, 4.6 centimeters, and a height of about 9.1 centimeters. Okay, in the next video, I will go over part B of this problem. Part B of this problem.